Okay, I'm going to show you in this lesson how to sketch functions when you are given information about the first and second derivatives. Don't forget just your general property or general rules here, although I shouldn't use the word rules, but whatever. If the derivative is positive, your function increases. If the derivative is negative, your function decreases. If your derivative is zero, you have a possible local extrema. F double prime positive, concave up. Oh, you can read all that stuff. Okay, I'm going to move on. If you're watching this video, you should already know these things. So, all right, so let's look at this first one. I want to sketch a function that meets all of this criteria. And looking at this, it says first, the derivative is positive between negative 2 and 3, which means my function will be increasing. That's just my little note. Arrows are not an acceptable answer, but it's okay to use those as a way of thinking. F prime is less than 0 means my function will be decreasing. F prime equals 0 means we are temporarily horizontal. So I'm just put a little dash there with a slope of 0. If the second derivative is positive, that means your function is concave up, which looks like a U. Second derivative is negative, that means your function is concave down, which means you're looking kind of like an N. So now we need to tie all of that into a single graph. So I'll do my axes here. Let's see, I have negative 2 and 3, so I do need both sides of the y-axis. And I'll throw in my own little scale, so I need to go to negative 2. So there's negative 1, negative 2, go over to positive 3 at least, because I do have information about positive 3. And I guess I'll go on negative 3 and negative 4. All right. Now, between x coordinates of negative 2 and 3, my function will be increasing. How I like to denote that or make note of that for myself is I put a little indicator up here that between negative 2 and 3, my function will be going up. Now my function is decreasing between negative, or to the left of negative 2 and to the right of positive 3. So everywhere where x is less than negative 2, my function is decreasing. Everywhere after 3, my function, is decreasing. You're good? So we're going down, then up, then down. Now let's factor in the concavity. I'm going to come back to the f prime equals 0 in a second. My second derivative is positive when x is less than 0. So that means all of this area to the left of the y-axis, my function will be concave up. And then when x is greater than 0, my second derivative is negative. So that means everything over here, my function is concave down. And then I'm making note that my slope is supposed to be 0 at negative 2 and at 3. So just a little note to myself that my slope is 0 at negative 2 and at 3. Now we need to piece all of this together. My function is going to go down to the left of negative 2, but at the same time is going to be concave up. So it doesn't need to be linear. I need to be decreasing while concave up. And then when I get to negative 2, I should have a slope of 0. So I'm going to decrease while concave up, and by the time I get to negative 2, I should have a slope of 0. So I made sure I got to a 0 slope when I got to negative 2. Then my function is increasing after that, but I'm still concave up until I hit the y-axis. So I'm going to continue that same trend, concave up, until I hit the y-axis. And at the y-axis is when I swap to concave down, which means that is an inflection point. Anytime you change concavity, that's an inflection point. So I'm concave up, then I'm increasing concave up. I'm still increasing, but now I'm going to flip to concave down. So I'm going to increase concave down, and I need to have a slope of 0 when I get to 3. And then after 3, I will be decreasing while maintaining concave down. So your function is going to look something like this. Now, I did not give you any actual ordered pairs to hit, so there's a little bit of leeway in how the vertical shift of this graph, but you should have something in this ballpark for those descriptions. Let's look at the next one. A little bit more information here, I think. Let's see, f prime is positive, means my function will be increasing. F prime is negative, means my function will be decreasing. F prime equals 0 means we're temporarily horizontal, slope is 0. F prime does not exist at 0. I'm going to come back to that one in a second. F double prime is less than 0. It means function's concave down everywhere except at 0. And then I give you just a straight up ordered pair to hit. I need to make sure that my graph hits the point 0, 0. It goes through the origin. Back to F prime does not exist. There are 3 places where a derivative does not exist. It could be a corner or a cusp. It could be a discontinuity, or it could be a vertical tangent. The vertical tangent is rare. You still need to be aware of it, but typically you will have corners or cusps or discontinuities when the derivative does not exist. So I'm keeping that in mind, and now let's see if we can sketch this. So let's see, it looks like -2 and +2 are my interesting points. So I'm going to go -1, -2, and I guess I'll carry on to -3. 1, 2, 3. And to the left of -2 and after +2, my function's increasing. So from -2 to the left, my function's going to increase, and from +2 to the right, my function's going to increase. Then between, oh wait, that's not right. That's not right. I'm so stupid. It's from 0 to 2, so I need to move that over here. So from 0 to 2, my function increases, and then from -2 to 0, my derivative was negative, my function will decrease, and then we decrease again when x is larger than 2. We do have 0 slopes at -2 and 2, so I'm going to make a little note that I have a 0 slope here and a 0 slope here. Then concavity. I am concave down everywhere but 0. So to the left of my y-axis, my function's concave down, and to the right of the y-axis, my function's concave down. And then finally, I need to make sure that I actually hit the point 0, 0. Remember that 0, 0 is where, or x equals 0 is where my derivative does not exist. And since my function is defined, I actually have a point there. I am leaning towards a corner or a cusp. That's what I'm leaning towards, although there may be other options. So let's see. I'm start by going up, then I'm going to go down, then I'm going to go up, then I'm going to go down. So I'm going up, down is my general trend, but let's factor in the concavity as well. So I'm going to go up with a concave down shape, then I'm going to go down with a concave down shape with a slope of 0 at -2. That's going to look something like this. Up, 0 slope at -2, down. I need to hit the origin because I was told to hit the ordered pair 0, 0. Then I swap to increasing, and right now I'm going to go with the cusp option, because if I go to increasing while remaining my concave down shape, that's going to give me that cusp. I need to have a 0 slope at 2, and then I need to decrease while being concave down. There are a couple of other options we could have had here because I didn't specify that the function must be continuous. I could have had a jump discontinuity and done something like this. If I had done that, I still have the point 0, 0 as part of my graph. I'm still concave down and have the correct points increasing and decreasing interval. Only this time, if I do it this way with the discontinuity, then the function is not differentiable at 0 because of a jump discontinuity. However, I just like the appearance of a cusp, so I'm going to stick with this one. There are a lot of times where you have multiple options in how you choose to graph these functions. So there is the second one, and I had just one more. And the last one doesn't have very many options, but let's take a look at this. We know that f prime is equal to 1. Ooh, f prime equals 1. Well, that means that for all negative x's, the slope of this graph is 1. My derivative is negative for all positive x's. That means my function will be decreasing. And my second derivative is negative for all positive x's, which means concave down. So let's look at this one. Not a whole lot of information given on this one. The only x coordinate that is of any interest to me is 0. I didn't give you any information about -1, -2, or any positive x's. What I do know is that all of this space to the left of 0, I have a slope of 1. and all of this to the right of 0 when x was greater than 0, we have a negative slope. So I'm going to go down. Here I have a slope of 1, and then my function is going to be concave down everywhere after 0. Okay? Well, if your function has a constant slope of 1, that means everywhere to the left of the y-axis is linear. So I'm actually going to graph a line with a slope of 1. A slope of 1 looks something like this. And I can put it anywhere because unlike the last problem where I told you we had to hit the point 0, 0, I did not give you any actual points for the function. So that gives us a little bit of freedom for where we want to put our graph. So I'm increasing with a slope of 1 until I get to this point, and then I need to start decreasing while being concave down. So now I'm going to go from a slope of 1 to immediately decreasing while concave down. So I'm going to do that by decreasing while concave down. Notice that is not a very exaggerated concave down, but it is still concave down. If it makes you feel better, then you can make it a little bit more bendy. You can do something more like that. I don't know, that's not a whole lot different, is it? But there you go. Function increases with a slope of 1, then we swap to decreasing and concave down, and that is what this graph will look like. So there is using derivative and second derivative information to sketch graphs. Hopefully that makes a little bit of sense to you.